Okay, welcome everyone to our fifth session on the relation of the science of physics to theology. And let's begin with a word of prayer. Dear Lord, thank you for letting us come together once again to consider the way you have made your orderly universe and how you are revealing yourself to us through it. We pray you will guide us in all things. In Jesus' name, amen. I have a verse, 1 John 2:17 here. The world and everything in it that people desire is passing away, but those who do the will of God live forever. The reason I picked that verse is because that thing about the world is passing away, what we're going to be studying today is called the second law of thermodynamics, and that's very close to the idea that everything is passing away. So, we will then give you a little summary of what's to come today. When you convert work into heat, by friction, for example, remember we talked about boring cannons, and that was how they discovered that mechanical energy and heat were equivalent. It's irreversible. You can't get all that work back again. You can't turn the heat all back into work. You can turn some of it back into work, but not all of it. This is summarized in something called the second law of thermodynamics, and there's a new term called entropy that's introduced in order to quantify this behavior, to put numbers on it. Entropy always increases, an interesting feature. Remember that energy stays fixed, doesn't change, but entropy always increases. And this turns out to have profound philosophical and theological consequences, which is the whole point of this. Okay, reviewing what we've done in the past, we remember that all of this is based on the fact that the creation is knowable and stable, and what God does is unchanging and non-contradictory. We can use mathematics to predict the motion of objects with very high precision. Mechanics can explain heat and temperature as well. Conservation of energy is found to hold when you add heat as a form of energy. And conservation of energy has some deep philosophical roots also. And it's easy to assume that this law of conservation of energy is absolute truth. In fact, whenever a scientist finds some experiment where it looks like energy is not conserved, he will go ahead and invent some new thing in order to make it conserved. That's how things like the neutrino were discovered, for example, that there's some energy that some of these nuclear reactions is getting away from us. It must be going somewhere. Oh, there must be something doing it. We'll call it a neutrino. All right, thermodynamics, the study of heat, maybe heat in motion for the dynamics part of the word. The zeroth law, we discussed last time, two objects having the same temperature as the third have the same temperature as each other. Okay? The first law is synonymous to the law of conservation of energy, and in parentheses I say the conservation of energy says you can't get ahead. There's only so much you have, all right? But now the second law of thermodynamics says this: some work is irreversibly lost when converted to heat. You can't even get even. Okay, so those are the ways to remember those thermodynamic laws. Now, a heat engine is a device that enables us to get work from heat energy, and that example is passed out on the sheet to you, the same as what's showing up there. And the idea it works is this: there's some high temperature thing, okay, we call it a reservoir, but it could be like a fire in a boiler or gasoline burning in your car engine, whatever it is, there's something that makes high temperature available. It goes into this thing we call a heat engine, and it gives out mechanical work, but it also has to discharge some thermal energy into some lower temperature source called a cold reservoir. And if that was your car, that'd be the radiator that's putting out heat. we will look at an example of a steam engine and see how, or I should say a steam turbine engine in a minute here that will give some more details on that. But first I want to point out that you can run one of these backwards. If you reverse all the arrows, you get a refrigerator. And you get taking heat out of the low temperature, putting work into the engine, and discharging it into the higher temperature. But you note you're going to be discharging more heat into the higher temperature than you take out of the lower temperature because you have to put the work in. So the refrigerator is using work to move heat from low temperature to high temperature. And a refrigerator can be used as an air conditioner, obviously. And if you just reverse it, you can make a heat pump out of it. And this can be the outside air and this the inside air. So those are all very useful things. But what we're trying to get at is the basic ideas. I'm running ahead of myself because here I have it in writing. But the heat engine works in this way. It takes the energy from the high temperature source, does mechanical work, transforms some of it to the lower source. And steam engines, internal combustion engines are complicated examples, not as simple as this little diagram. So here is a complicated example called a steam engine, and it could be a steam turbine in a power plant. But what we have is a higher temperature source, which in general will be a flame of some kind, a combustion. Heat is transferred into a device called a boiler where water is boiled. And in order to get the water to boil, you pump the water into the boiler with a pump that raises it to a high pressure. It boils at a high pressure, which means also a high temperature, and out comes high pressure, high temperature steam. This high temperature steam goes into a steam turbine, and the steam turbine is a device then that gives out mechanical work, and out of it comes low temperature, low pressure steam, but still steam. Part of that work goes back to run the pump, and the other part of the work could be running, say, an electrical generator or whatever it is you want to use for your output. But in order to get the water back again, you have to go through a thing called a condenser, which has to be cooled by some lower temperature source to take the extra heat out of the steam and turn it back into water. The water then at the low pressure feeds back into the pump, raising it to high pressure, and around the circle it goes. So we're not consuming any water in this. Now you may think about a steam locomotive, and how's that different? Well, it doesn't recapture it. It has to keep putting in new water, and it puffs the old steam out the stack rather than condensing it. So it's an open system instead of a closed system like this is, but it's still the same idea. So all basic steam engines work in that way. Now, the heat engine is the way to get the work of energy. And as I said before, air conditioners, refrigerators, heat engines operated in reverse. And here comes the big question. Why can't we eliminate the discharge of the heat into the low temperature? Well, if we could, the thing that we would get would be called a perpetual motion machine of the second kind. Have you heard of perpetual motion machines? They're devices that just go on their own, all right, never need any input. Well, they don't exist in practice. And in fact, the patent office said a long time ago that if you want to patent a perpetual motion machine, you have to bring a working model of it to show us. And that gets rid of that. Well, this perpetual motion machine of the second kind would take heat from a single source and turn it into work. And if you could do that, you could do wonderful things, like send a ship across the ocean, powering it by taking heat out of the ocean itself to run its engine. That would be easy. Okay, wonderful if you could do that. It wouldn't violate the law of conservation of energy. The first law would be fine with it. But it never happens, and because it never happens, we say there's a law that forbids it, and it's called the second law of thermodynamics. Okay. Now, you can say the second law of dynamics in words like this. It's impossible to build any device whose sole effect is the extraction of heat energy from a reservoir at one temperature and the performance of an equivalent amount of work. In other words, you can't have the ship sail across the ocean using heat out of the ocean. Another way to say it, it's impossible to build a device which has no other effect than transferring thermal energy from a cold body to a hot body. Heat always goes from hot to cold, it doesn't go the other way. And you can't make something that'll do it unless you put work into it and make it into a refrigerator. These two statements are equivalent, as it turns out, and they summarize many, many, many experiments. It's not something that came about lightly, okay? Now, there's a limit on the efficiency that you can get out of one of these heat engines. In other words, if you have to put some of the heat into the low temperature side, how small can you make it? Okay, well, the answer, you can show that the amount that you put into the low temperature, which we call Q low, has to be equal to or greater than the amount you take out of the high temperature multiplied by the ratio of the temperatures, the low divided by high, which is a number that's always smaller than 1, okay? And these temperatures have to be measured on the absolute scale. You know, we talked about that last time, absolute scale of temperature, which is Fahrenheit minus 460 or Celsius minus 273 degrees. The limit on the efficiency, let's call the efficiency little e, it's the work you get out of the engine divided by Q high. The way I was told to remember this a long time ago was, efficiency is always what you get that you want divided by what you have to give that you pay for. Okay, so we want to get work, we have to give up heat from our high energy or high temperature source. And so that ratio is the efficiency of the engine. Okay, well the work is the difference between the heat that comes out of the high and the heat that goes into the low. Okay, so we can substitute that in the previous equation and say the efficiency is Q high minus Q low over Q high. Dividing it out as 1 minus Q low over Q high. And remembering back to our previous page, T low over T high has to be greater than Q low over Q high. So when you put it in here, it turns the inequality around, and you get that the efficiency then is less than 1 minus T low over T high. So the highest efficiency occurs when that ratio is the smallest. In other words, you've got the biggest difference between the low temperature and the high temperature. So when you're building a power plant, you want to have the high temperature be as high as possible and the cooling end of it be as low as possible. All right? And that's the limit. That's the perfect limit. Ordinarily, you're going to have an efficiency that's somewhat lower than that. And that's the job of the engineer, mechanical engineers in particular, figure out how to get as close as you can to that efficiency from the engine. All right. Now, the second law of thermodynamics, in order to make it like the first law, where we have energy that we can measure, foot-pounds, remember, force times distance, entropy is a number that we're going to invent to quantify the second law of thermodynamics. The new word, it sounds a little bit like energy. It hasn't made it into popular vocabulary like energy has, at least not so much. Entropy is defined by how it changes. Okay? How does it change? Well, if you, we'll get to that in a minute, but here is the idea that a particular mass of a substance at some temperature has a certain value of entropy, and we give that entropy the symbol S. It'll be a number, all right? Where we get the number is by changes. If you add an amount of heat, delta Q into a body, and divide it by the body's temperature, the body's entropy changes by delta S, delta Q divided by delta T. All right, so if we add an amount of heat, and how do you measure heat? Well, you could measure heat in the same units you measure work, as foot-pounds, or kilogram meters or something like that. Or you could also have heat units like calories, if everybody knows about calories. But you have to have some kind of unit, and in that unit you have delta Q, and then T is in temperature in degrees, and it would be in degrees Kelvin, perhaps. That's the absolute temperature scale based on centigrade. So you would have joules per Kelvin as a unit for entropy. Okay, well now, if you remove heat from something, the entropy is reduced in the same way by the amount of heat out divided by the temperature. So now, the interesting thing is, if you have two bodies transferring heat between them, the net change in entropy, the total change, is this difference. The amount of heat divided by 1 over the low temperature, that's where it goes in, minus 1 over the high temperature, which is where it goes out, and that's always going to end up being greater than or equal to 0, since the high temperature has to be equal to or greater than the low temperature. And 1 divided by a small number is bigger than 1 divided by a large number. So that's always positive. The change in entropy, whenever heat is transferred, is always a positive number, because you can't transfer any heat unless that's greater than. If it's equal, nothing happens. Now, engineers like to play with the idea in their calculations that you could actually get the equal sign here. But you never actually get it. But the way you get it is getting closer and closer and closer to it by bringing the temperatures closer and closer and closer together. Finally, they get so tinily far apart, like 0.999999, something like that, that you say for all practical purposes it looks like it's conserved. And when you do that, that's called a quasi-static process, because the speed at which it would go would also stretch out infinitely long, because there's very little temperature difference to drive the reaction. Okay. Well, as we said, in the real world, since you can only go from hotter to colder, there's always going to be an increase in entropy. Oh, well, that's interesting. It's a quantity that always gets bigger. Another way to state the second law of thermodynamics is to say the total entropy of a closed system never decreases. Now, that word closed system is important because we're assuming that we are having our discussion about a situation where we know what everything is and what all of its temperatures are and all those kind of things. We're not talking about open systems where stuff can come in from outside, bringing in new energy sources and could change things. But in a closed system, it does not decrease. Note how entropy never decreases leads to the limit on the heat engine efficiency. We had the formula for the heat engine efficiency before, but now if we look at it from the standpoint of the low temperature over the low heat over the low temperature, it has to be greater than the high heat over the high temperature, because that's just the second law of thermodynamics. The entropy in the hot reservoir is going to go down when the heat comes out. The entropy into the cold reservoir has to go up when it goes in, and the amount that goes up has to be more than the amount that went down to satisfy the second law, so we get that equation. And then when you substitute that into the equation on the efficiency of the engine, you end up getting this result, which is the one that we started out with before on that. So the efficiency limit on the engine is because the entropy has to keep increasing. You can work on the algebra on your own time, okay? Sherry. Okay. It is it's a concept. Energy is a concept too. Well, entropy is also very real. It's a number that's associated with a substance. In fact, if you were to look on the engineer's steam tables, which they use for designing machines, you will find that one of the coordinates is the entropy and another coordinate is the energy. And you draw curves based on those two things. It's a property that a substance has. This remote control has a certain amount of energy associated with it and a certain amount of entropy associated with it at a given temperature.
What's the entropy associated with it?
How would I get the number for it?
Or how would you describe that?
Well, if I knew the material it was made of and I had all these tables that represented, I would know that at a given temperature it has a certain entropy because it's related to the temperature and the material properties. But it is a number that you will find for substances when you get into doing calculations on them. And those numbers are then used in the calculations. It's a variable that goes in the formulas for studying materials in thermodynamic reactions. And that may not explain it too well, but it's sort of... Other questions at this point? I really meant to ask earlier if there were leftover questions from last time, but I didn't. But if you have a question now, bring it. Okay. The next subject is the microscopic view. Remember, we had a microscopic view of heat as being the kinetic energy of the molecules moving around in a gas, flying back and forth, or vibrating in a solid. Well, there's also a microscopic view for entropy. Heat is, on the microscopic scale, is this motion of particles. Entropy on the microscopic scale is related to the number of ways these particles could have their total energy distributed among them. Okay, think about that a little bit. If I had X amount of energy and I had two molecules, I could let this one have so much and this one have so much, but then I could take some from this and give it to this, and so back and forth. There'd be different ways you could distribute the energy. When we have these huge numbers of particles, like 10 to the 23rd gas molecules floating around, there's a very large number of ways you can arrange the energy among them. And the hotter the temperature, the more the ways are you can arrange them, and the higher the entropy. So in the entropy, in a certain way, is a probability statement for an arrangement, okay? And this gets into technicalities I don't want to go into here, but it involves logarithm of the probability of the states, etc. So it's also closely related to information theory, which is another area where the word entropy also comes up for any of you who are electrical engineers out there. Anybody? Oh, well, yes, sir. Okay, if the particles have zero energy, and this is in classical mechanics, you can't do that in quantum mechanics, but if they did, they'd all be stopped. And there's only one way you can distribute zero energy among any number of particles. They all have zero. Okay? So there's probability 1, and that probability 1, taking a logarithm, you get 0. For those of you who know that kind of math, log of 1 is 0. So the entropy is 0. So the 0th law of thermodynamics is we take entropy to be 0 when temperature is 0. That's the starting point. And when the temperature goes up, the entropy goes up. Okay. Well, that's just a 0 point, as I said. Now, okay, here's what we're waiting for. What are the philosophical consequences of all this stuff? If you believe that heat always goes from hotter to colder and entropy never decreases, then eventually the entire universe comes to the same temperature and nothing more can ever happen. Okay, that is referred to as the heat death. It was recognized early on by the scientists who were discovering this stuff, and one named Clausius is sometimes called the Clausius heat death. And that's the ultimate pessimistic view. The end of everything is everything comes the same temperature. Well, today we have the cosmology view of the universe and all this kind of stuff. Maybe it expands forever, maybe it contracts, but at some point it ends. and it ends in a very unexciting way. The universe goes out with a whimper instead of a bang, according to this. Just everything winds down. The ultimate pessimistic view. Now, here we have the next part. The first law, conservation of energy, if it's an absolute, then total energy is eternal. Never changes the amount of energy we have. Okay? The second law, if it's absolute, says the universe is only a finite time old. Why? Well, look around. We're not all at the same temperature yet. So it hasn't been an infinite amount of time. There's a problem between those two. They contradict. They can't both be true. If they are both true, then something had to happen from outside of this universe system to make it happen. And that's God. Okay? So that's your philosophical proof for the existence of God. The two laws of thermodynamics, the first and the second, if we're both absolutely true, they contradict each other. As far as we know, they're both absolutely true from our experiments. That means something has to act outside of this order that we have here to change something to allow the current situation to exist. Okay. Now, I could get into a lot more discussion about what that would have to be, but essentially, you know, God has to either create the energy at some time that isn't eternal, or if it's been there all along, it must have been in a static situation for an infinite amount of time, and God had to do something to get it start moving. So either way, you have to have this action from outside the universe as we know it for the universe as we know it to exist as it does today. Okay, that's my proof. Other people could perhaps argue about it, but I sort of like it. The paradox of irreversibility. Now, here's an interesting thing. Newton's laws of motion are reversible, but conversion of work to heat is not reversible. There's this always increase in entropy. So how are we going to reconcile those? Okay, this is the next little problem. Examples of irreversibility. I didn't get it done. I meant to bring out a glass and put an ice cube in it and let it be sitting here all the time I was talking. And if I had, you would have found that the ice was melting. Now, it would be equally okay, according to the law of conservation of energy, if the ice got bigger and the water boiled off some of it. But we don't see that happening. It's an irreversible direction that it goes. The ice always melts and the water gets colder. Breaking eggs. You can break an egg. Have you ever seen an egg put itself back together again? Nope. Well, I'm going to show you one. Just for a second here. Excuse me, I have to play with my system and get us to a different file. And full screen. Toggle full screen. You didn't toggle. There we go. Here we go. Eggs breaking in slow motion. This came from YouTube. Come on here. Here we go. Oh, they broke. Eggs are broken. All right. That's about what you would expect to see, some eggs breaking. Trying to get rid of that display. Want to. Okay. Breaking is normal. Unbreaking is not observed, but it's permitted by Newton's law. So look here. The eggs are going to unbreak. Give them a little time. There we go. We're starting to get back together again. Let's get the shells back on. Now let's go up. Okay. That doesn't happen, right? That's what makes it cute. But we will now go back to the preceding attractions. And of course, it's going to want to start at the beginning. So I will very quickly get us to the end. Okay, well, can we think of any other irreversible things that we might want to look at? Unbreaking of eggs was one. Let's talk about biology for a minute. I'm not a biologist, but we know that organisms like humans seem to violate the second law. We do creative things, we make order out of disorder and all this. And so you could argue that in the biological world, we don't see this law of conservation or the increase of entropy always working. Well, the catch to that one is, if you think about it, is the biological system is not a closed system. There is energy coming in from the sun that makes it all possible. If we didn't have that, we would not have any life. And the increase in entropy in this heat production and transfer from the sun is going to be bigger than the decrease in entropy from all of our creative work. Now that's a philosophical viewpoint. Obviously, nobody has done all the experiments necessarily to show that. And when they do, they get into an area that's called non-equilibrium thermodynamics, which is another study altogether, because all of this work on conservation laws and entropy definition assumes what we call thermal equilibrium of the objects we're studying. Meaning that if you have a device and you say that it has a given temperature, that means that the molecules in it have a distribution of their energies that satisfies a certain nice bell-shaped curve, kind of statistical distribution. And if you don't have that, it's not an equilibrium, but it will come there very quickly. But at any rate, that's a much more complicated thing. After biology, we have another little character that comes along trying to get over the paradox. He's called Maxwell's Demon. Now, to explain Maxwell's Demon, I have to draw us a picture here that I don't have on slides. And it's an experiment that I want to do. I'm going to have a nice big box, and I'm going to fill it full of a gas. I'm going to have a little door like up here on the top of the box. And I'm going to put I'm not going to fill it full of gas. I'm going to put a barrier down there in 3 dimensions. You know, it's like a rectangle, and here's a piece that I've slid in to block it. Now I'm going to fill this side up with gas, and this side is going to still be a vacuum. If I were to calculate the entropy of that system, I get a number for it. Over here, it'd be a number. I don't know what the number would be, 523 calories per Kelvin or something. There's a number for the entropy of that gas. Now, I'm going to grab this little thing, and I'm going to pull it out so that my wall is up here, and the gas all at once fills the vacuum. When it does that, and I recalculate the entropy has gone up because the molecules now have more places they can be, so there are more ways they can be distributed, so that number associating with entropy has increased. And I got no work out of that. No work from that expansion into a vacuum. Okay, so that's an irreversible event. But here's the idea of how we could reverse the event. We now have gas all over in here, and we put our wall back in, but we have a little trap door in the wall here. And we have a little character in here that's called Maxwell's Demon. And Maxwell's Demon is watching. And whenever he sees a molecule of gas coming this way, he opens up the trap door and lets it through, and then closes it real fast. And after a while, he gets all the gas back over on the other side. He's reversed it. And he has caused entropy to decrease. And this caused a lot of concern among philosophers and scientists of saying, how do we explain Maxwell's Demon? And they finally get around to explaining it this way. The little guy has to know that it's coming in order to be able to open the door. And the very least information he could have to know it was coming would be to have a single photon of light come off of it up to him. And there'd be enough energy used that way, an increase in entropy, to overcome whatever you gained by letting it go through. So Maxwell's demon can't function because it has no way to know when to open the door. Okay? Well, that's another example of how entropy always gets bigger and you can't do anything about it. Now, where do we go from there? Well, we go on to the next class, and this one is getting us out of classical physics. All of this up to now has been what we call classical physics. It includes the mechanics of Newton, Newton's gravitational law, and the mechanical equivalence of heat, and the second law with the increase in entropy, and all of the philosophical ramifications that comes from that. But about the beginning of the 20th century, the tables start to get a little cloudy. And there were some experiments that were done, primarily with light, that indicated that maybe these laws don't always hold. And because of that, there was a little revolution that occurred in physics. And what came out of that is called modern physics, even though it's 124 years old about. But it's modern in a sense, and the other was classical. So the first thing we have to look about in that is the topic of light. And so we'll start out next time talking about waves and light and electromagnetics, which is a big subject all of its own. If you have any requests that you want, you can email me to that little email address. And you can also get those things from the website, not the website, the Dropbox site. The website that's in the church newsletter will have the videos that we're making of these presentations. There's a Dropbox that I have the written materials, these handouts, plus the files, PDF files that have these slides on them, so you can have those too. And there's some other stuff there that's, I think, maybe of interest to some of you. Okay, if you don't know how to get it, I thought I sent it out in an email to everybody earlier. If you don't have it, send me an email and I will send it back to you, the link. Any questions? Yes? Okay.
Would it be correct to understand that entropy is a measure of how much energy?
Say that a little again.
Would it be correct to understand entropy as a measure of how much energy would be that thing was involved?
I don't think so. Entropy is more likely a description of the amount of disorder in substance in its microscopic form, or it's just this quantity that's associated with a substance that always increases, but it doesn't tell you anything about how much heat you can get out of it. Theoretically, if you have an object that has a certain amount of thermal energy associated with heat energy, theoretically, you could turn all of that heat energy into work if you only had a zero temperature, lower temperature source. Because you remember the efficiency of the engine, it was T1 minus T low over T high. And if T low was 0, the efficiency would be 1. All the energy could go into work. So all you got to do now is get me a big hunk of stuff at absolute 0, and you can now have all the heat turned into work. But the second law says you can't do that. So the second law can also say the absolute 0 can never be attained. Because if you could attain it, you could violate the second law. So you have people doing stuff, and you might read about it, that they've gotten down to a temperature of 0.0001 degree above absolute 0, maybe, and they keep trying to get lower, but you just can't get to 0. Now, when we get on into the next weeks, we'll talk about quantum mechanics, and that complicates life even more, but it begins to explain some of this stuff because you can't ever get these molecules to stand still, okay? There's always what's called a 0-point energy associated with everything. And that's in the coming attractions, okay? Jerry.
So the first and second laws, are they based on a closed system?
No, they're based on you can have thermodynamics for an open system. You can talk about heat flowing in and out of the system, but it has to be going somewhere else. And if you enlarge what you call your system, eventually you'd make it closed. The whole universe is presumably a closed system. There's nothing outside it other than God, which we're trying to leave out of the discussion except to prove that he's there in order to do things. If you follow what I mean, yes, the Earth, for example, is not a closed system. It's open in that radiation comes into it and radiation leaves it. But on the other hand, if you were to take a bigger volume of the universe, you could see it's pretty well closed because the amount of radiation coming in and out is trivial when you were to put a big imaginary sphere around the solar system, that if it's big enough, what goes out is not all that much, and what comes in from the stars is not all that much, so it's approximately closed. But if you go for the whole universe, then it is closed. But the laws themselves, how do I say this? The entropy of a closed system never decreases, all right? An open system can obviously decrease because if I cool something, that something has its entropy decreased. It just went somewhere else. Does that make sense? Okay, any other discussions? Okay, well, as I said, next week we're going to shift gears a little bit, and we're going to spend most of the time talking about light and wave motion. And then the week after that, we will get into the quantum mechanics per se, for sure. And then the weeks after that, we'll talk about the theory of relativity, which is the other side of modern physics, because modern physics has two aspects. One is quantum mechanics, which comes about when you look at very tiny things. That's important. And the theory of relativity, which is important when you talk about things going very, very fast. Okay? And then there's the general theory of relativity, which is important when you talk about things that are very, very big. So all of that is yet to be discussed, and hopefully it will all, at some point, lead us to an affirmation that there's more to the existence that we know than just the created universe itself, but there has to be the spiritual side of things where God is, that is able not only to create but also to interact in the creation. Okay. Well, that's all I have to say for today. Anybody else have any further questions? Then we will have our closing prayer. Dear Lord, as we ponder this world that you have made, we see how great it is and how complex. We know that you are greater than all and that you understand all things, even as we struggle to learn and understand your creation. But we thank you that you give us the ability to do that, and that through it we can learn more about you and your great power and love for us. And we thank you for this in the name of Jesus, our Savior. Amen. All right, next week we try again.